Good afternoon, everybody. Thank you for coming and joining the Learning Lab 8 from the Cruise Data Science Initiative. This is a Zoom meeting, so what I'm going to ask you that if you can keep your mic and your video muted. So I'm going to do the presentation with the help of Daniel. And as soon as you start, as soon as I finish, so I'm going to open the room for questions. So please always keep muted. So I'm gonna just share my screen and then we are gonna start with it. Okay, so this is the talk for today. Just gonna turn off my video. I'm just gonna get the laser point. And that's what I'm going to be talking today. We're going to be talking about time series forecasting with SARIMA. So we are going to be a more technical talk about the SARIMA model for forecasting. And we're going to do an application with the COVID-19 pandemic data set that you're getting from the Johns Hopkins University. So just to start, the host of the talk today is going to be me, Marcelo Guarido. I'm a data science with a PhD in geophysics, and I'm the head of the Cruise Data Science Initiative. And Daniel Trett, he's a professor and he's associated with the University of Calgary. Daniel, would you like to present something about yourself?
Not much, except that I'm very happy to be helping Marcelo and learning quite a bit from his expertise.
Thank you. So for today's agenda, you guys are going to give an introduction. What is the Cruise Data Science Initiative and what you are doing, what type of work that you are doing in the University of Calgary. Then we're going to talk about time series and the decomposition of a time series. How can you represent a time series? And then we're going to start talking about the SARIMA model. SARIMA model is a combination of several methodologies, actually, like the autoregressive, that's the AR part, the integrated, the I, the moving average, that is the MA, and the seasonality, that's the part S. How we are going to be doing SARIMA in R? So we're going to be doing a coding session after the presentation, the PowerPoint, and some closing notes. So just for you to have an idea what you're going to be doing today, we're going to be using the R in the R Studio environment. And here you're going to be running and plotting all of our results that you're having here. So this is how you're going to be provided for you tomorrow or the day after tomorrow in the Cruise website, this code. So going back to the presentation, this is the Cruise Data Science Initiative. It's a new thing that you're doing in Cruise. Cruise is famous for the seismic research that we've been doing in the past. And now we are starting with our data science subgroup, where we're going to be doing data science projects that are going to be more focused on geoscience, but also open to other type of areas, to other areas. And they're going to be also doing academic and industry related projects. So they can be more academic, more theoretical, and more things like that, or more applied to real cases like in the industry. We also provide in the Cruise Data Science Initiative programming training. Programming can be basic programming in R, Python, and MATLAB, and also how to create applications, how to create apps with your coding, because a thing that you need to know as a data scientist is not only doing the science behind it, not only doing the data analysis and the modeling, you also have to deliver whatever you are creating. So in a way to deliver, in an easy way for everybody to understand, is to create an application. We're not going to create an app today, but in the older areas or the older learning labs that we did in the Cruise Data Science, you're going to see like how to create apps. And they also providing those learning labs. Those are free webinars that you do every 2 weeks. Sometimes we have a break for other reasons, but it's mainly every 2 weeks. And you can find all the information in the cruise website. If you click here in this link, that is not clicking because I'm in the pointer option. That's a laser, right? So I'm just going to turn this off so I can click here on the link. And here is the cruise website. And this is, if you go to the research links and the data science, you're going to have all the information from the previous labs. So you can download all the codes and have all the information that we did in the past in here. And also the future ones, they're going to be all included here all the time. So it's free and everybody can download. You don't need to register or anything. It's open to everybody. So I'm just going to go back to the presentation. That is not the presentation. Sorry, I might have to restart. And okay, so this is the cruise data science initiative. So now we gave a proper introduction to ourselves. So let's talk about time series and what time series are and what is the decomposition. So an example that worked in the past already is a time series. It's some kind of measurements that you take over time. In this example here, we have the WTI, the Western Texas Index crude oil price. This is the daily price of it from 2005 until someday, I think it was October 19th of this year. So this is a time series where we have the measurements for every day, what was the price of the oil. And talk about time series decomposition, a way that you can represent a time series is by dividing in several components of it, like this one. We can have the observed data set, that's the same time series that you have here. We can divide it into a trend, seasonality part, and the error. That would be the sum of those two, or the multiplication of those two in here, the trend and seasonality, and what is the remainder to the observed data set. And you can represent this type of decomposition in an additive decomposition or a multiplicative decomposition, where the XT is the observed data set, the MT is the trend. So it's basically, you can think this as a smooth version of the observed data, or even some algorithms, they're going to get like some changing points that's between two parts here. It's just going to do a linear regression. So that could be a linear trend between two spots in time. We have the seasonality, that's something that you can identify in your data set, something that repeats every 7 days, every month, or whatever. And the error, that's just whatever you need to include in here to make this sum equal to the original data set. Usually call this as a white noise. So this is a time series. So let's start talking about SARIMA model. So SARIMA, it's a combination, like we said before, of several other small methodologies inside here, like the AR, that is the autoregressive that we're going to talking about. So as I thought, it's going to be a little more technical. So we're going to go through a little bit of equations. So the autoregressive basically is just a linear regression over the past data set. So your XT is going to be just a linear combination where you have these parameters alpha, that are your regression parameters, of the past times of the time t-1, t-2, until the time t-p. So we are going to do a linear regression over p legs. What we call a leg is just one moment in the past. So that's a leg. We can represent this same equation in a polynomial order of p if you introduce this backward shift operator. It's just an operator that when you apply this operator to the data at time t, is going to be equal the first leg of it. Or if you do the shift operator of the exponential n is going to be just n legs in here. So this equation in here can be represented as this polynomial order. So we have this theta of b in the time series. It's just going to be this linear combination, the same alphas that we have here, of the xt, and each one of them is going to be multiplied by this operator. And that's going to be equal the noise. So that's what you're expecting. You wanted to find this in a way that's going to be equal the noise. So this is just an example of when you have some kind of a time series in here in red. And this is just the autoregressive with order 14. So it got 14 points in the past and did a linear regression. So probably this is something that's a daily measured. So 14 is basically 2 weeks that you're observing. So that's the blue on the back. That's the autoregressive part. So the next part that we have to talk is the moving average of the SARIMA. So it's going to be also quite similar, but what you're going to be doing is a linear combination on the noise part. So what you want to do is basically want to smooth the time series. It's a way to apply some kind of a smooth to make it more to filter a little bit of the noise. So it's the same way it can be represented on the same backshift operator, and it's gonna be like the xt. It's gonna be like the combination on the noise that is gonna have this formulation. So it's the B order key. So this order Q we have to remember, because those are gonna be the parameters that you're gonna be finding on the SARIMA model. So if you just combine the autoregressive and the moving average, we are going to have a model called ARIMA. And always we have to decide 2 parameters for this model. The P, that's the order of the autoregressive, and the Q, that's just the order of the moving average. So just a plot here for an example of what is a moving average. We have like this stock index in blue, and this is the moving average for 15 days. So basically, it's going to get 15 days of your original data set and calculate an average of this one. And then you're going to move a little bit and calculate the next average for 15 days. So we are smoothing this. And you can have a shift like that. Larger the moving average, larger the window for the moving average, more shifted it's going to be. Smaller, less shifted, but less smooth is going to be as well. The next part that we're going to talk about is the integrated, the I part. This is an introduction, usually for the ARIMA part, where the forecasting, it works better when your time series is stationary. What means stationary? It means that you don't have any trend, or it should be around a constant number, all your variations. So this is an example of a time series that actually has a trend. So it's increasing over time. So it's called to be a non-stationary time series. So what we do from the integrated part is to calculate the difference of the data set. So 1 point minus the other, 1 point minus the other. So it's just a differentiation. And when you apply a differentiation on these data sets, we get this. We get a data set that don't have the trend. So now we call this data set as stationary. So when you combine those 3 that you have until now, the autoregressive, the integrated, and the moving average, we can do a type of forecast named ARIMA, and they're going to have the parameters P, D, and Q. P means the order of the polynomial for the autoregressive. D is how many times I have to differentiate the data to make it become stationary. Because in the example that we did here, basically just one time, just one differentiation made this time series to be stationary. But sometimes you need to differentiate more other times as well. So it could be 2 or 3. So this parameter might change, depends of your time series. So just going back, and the Q is the moving average. So what's the size of the window, basically, that you're doing to calculate your moving average. We call this a ARIMA model. That's just a combination of these 3 equations that you had before. So when you have the parameters P, T, and Q determined, we can see what's going to be the future of this time series. In this example here, it's a ARIMA model that didn't require any autoregressive, so the order was 0. It required, for this time series, 1 differentiation and 1 moving average. And this is the prediction that you have with ARIMA model. The only thing with the ARIMA model is that it's going to be strictly linear, the predictions that you're going to have. We have no seasonality included yet in here. So that's the part that comes with the S, the seasonality for the SARIMA. And this is an example of how a SARIMA is going to do your predictions. So if you have a time series that you have seasonality, we have the trend, and you have everything, you should get forecasting following this orange line. And for that, we have to, in that equation of the SARIMA, to include the seasonality. And in a very similar way, we have to include the parameters PDQ that we had for the linear part. We had to include those uppercase PDQ for the seasonal part as well. And this S is going to be what's the number of seasonal points that we have. If it's 7 days, our seasonality. If you have a data set that's daily measured and your seasonality is 7 days, so this number is going to be 7. And that's the following equation that you're going to have for this for the SARIMA model. It's a little complicated, but what you're going to do, you're going to learn how to apply this SARIMA. To determine all these parameters, it's quite hard. We have to do a lot of analysis, correlation, and tests. However, there are some libraries that help us a lot with that. Most specifically, there is a package named ARIMA, or in R, that's going to calculate this for you based on some metric. In Python is the SARIMA X that does this for you. But we're going to be talking about the SARIMA in R, and more specifically, the library Modeltime, where we're going to show how it works. So Modeltime, it's a library that was created by Matt Duncan, and you can access the website in here. It's a type of library that follows the same way as the tidy models. For the people that doesn't know tidy models, the tidy models would be the equivalent of the scikit-learn for R, where you have a groupment of different methodologies in more than one package. One problem in R is that you can find any solution, any library that can help you with your problem, any model, for example. But they are from different libraries, and sometimes to find them all, it's quite hard. So we have this tidy initiative, like the tidyverse and tidy models. They are trying to aggregate all those libraries in one. So when you load the tidyverse library, you're going to have a lot of libraries that are going to be loaded in the background for visualization, for data analysis, for data manipulation. For the tidy models, it's going to be loading a lot of libraries related to machine learning. And this Modeltime follows the same idea of the tidy models, but for data forecasting for time series. So you're going to have models like ARIMA, the Facebook Prophet, and several others. If you go here to the website of the tidy models, you can find like all the how you do the installation. You can find some examples. You have videos. If you go to documentation in here, you get the getting started with the Modeltime. So you're going to have some simple examples and how to do all the plots and everything, all the analysis. So that's a pretty good library, and I really recommend to use that. And for our research today, our coding today. We're going to be using the tidyverse, the tidy models, Modeltime, the Calibrate library. It's one to deal with dates, a library to deal with dates, and the Plotly to do our figures and our plots. And those are iterative plots. So let's go for the coding. So I'm gonna start open here my R section. So this is the R Markdown environment. So if you wanted to use R, I really recommend for you to use the R Studio to compile your codes. So if you want to use R, you have to first install the compiler, that's the R project, and then you have to install some editor for the R. So I'm using this R Studio. So this is just a simple R code, and that's gonna be the only file that's gonna be provided for you. And let's go for all the things that you're gonna use here. So to run any specific area, you can come to the row that you're gonna run it and press Control Enter. So you can see now it's run here in the console, means that I'm loading the library tidyverse now. And that's how we're going to be loading libraries. So we call the function library, and inside it, the name of the library. It's very similar to the Python where you do import a library. Or another way to run, you can select all the things that you want to run at once and do the Control Enter. So it's going to run both in here. So now I'm loading the table. It's a better way to do data frames in R, and the Calibrate for the dates. And now another things for the models. Now we're going to be using the Modeltime and the tidy models. So we're going to be loading this one, the library Plotly, and sometimes it's nice to use this time 2K. That's the same for the same creator of the Modeltime. It's a library for time series visualization, but I don't believe I'm using this a lot. So I'm just loading here, so you know. The data set that we are using here for our analysis, it's being downloaded from the COVID-19 data repository from the Johns Hopkins University. So it's a GitHub repository. So you can even find here in this GitHub, you can find all the data that we need for this to create this dashboard or for create your analysis. And I believe that is this one that you're inside. And let me just remember. Oh, no. So COVID-19 should be in the raw. Well, it's somewhere here. I apologize for that. So what I'm doing in here, I know what's the link to the CSV file inside the LinkedIn. So when I do the read CSV, that's just a way to load your CSV files or your tables that you are saving in CSV. You can include a URL in here. So it's going to go to the internet and download and load it for you automatically. Some things that you have to remember in R, that this symbol here, it's the same as equal, but for historical reasons, I'm using this one. In the beginning of R, you didn't have equal to assign a variable to something. And these pipes in here, this symbol, like the percentage, larger and percentage, it's named pipe, and it's very similar to a Linux coding when you do a pipe, grep, pipe, and cat, for example. So the output of this one is going to run in this next function. And everything that you run here is going to be received in here. So for example, if you just run this part in here, we can just select this one and run. So what this read CSV is doing is downloading the data set, you can see here, and it's plotting. So it's downloading a table that's in basically a ASCII format in here. And what I'm doing here for this next part, I'm converting to a table. What it means, I'm converting to a data frame. So when I download and run, now I have a data frame in here. So it's going to have this format. We have a name of the column, all the information in the rows, and what type of information that we have here, if it's a character, if it's a double, integer, and so on. So what I'm doing here, I'm just gonna save this in this df_cases. So what I'm downloading here, I'm downloading the cases of COVID-19 per date. So now I created this data frame. So if you click here, you can open the data frame. So we have the table, and that's the information that we have. We have the province. If you have like some countries, it's going to be divided by province, the information. You have the name of the country. You have the location, basically the central location of the country. And this is the time series for each day, how many cases you had activity there. And this is a cumulative data frame. So when you pass time, it's always going to be increasing. So you have one case here. So you didn't have new case until this day. It means now you had 2 cases in the country, 3 in the country 4. So this number is always going to be increasing. So this is cumulative. And this is a data frame for the number of cases. And this one, we're going to be downloading by the death. How many people died for the COVID. So we're going to do similar way. We saved in another data frame here, the data frame underscore death. And you have basically the same information. We have the country that you want to see, what's the information, sometimes divided by province. So if you want to study the country by itself, you have to stack this information. And if you want to understand what's the number of new cases per day, we also have to calculate a differentiation here. And that's what you're going to do. In here, I selected in a way that you're going to work with one specific country. And Daniel, okay, are you there? Daniel?
Yes, I'm here.
Which country do you want to work with?
Well, let's try Argentina then.
Okay, so Daniel is from Argentina, so we're going to do Argentina. So that's the country. If you go here to the DF cases, so you just have to make sure that you have the country here, probably yes, because this is an official data set. So it's here in the row 7. So we have Argentina in the data set. So now we are just selecting the country is Argentina. And in this part of the coding, what I'm doing, I'm selecting only the rows where the country region, that column country region is equal, the country is equal Argentina. So I'm just going to be selecting in here, these DF cases, this row 7, basically. So if I just run this part in here, that's what you're going to have. Basically, you're going to have an array. You're still going to have a data frame, actually, with all those information and the time series, but only for Argentina now. And the next part in here, I'm just removing some rows that I don't want to work with. So I don't want to work with the province state anymore, because now I know this is just Argentina. I don't want to work with the province state and the country region. And I don't want to work with the latitude and longitude. Means I'm only going to have the time series. So I'm selecting, and this minus means that I'm selecting out these 4 columns. So if I run this, you're going to see. Let me just make this a little bigger, maybe easier to see. Now I don't have those initial 4 columns. So now I just have the time series. But something that came weird when you download the data and load here in the R is that the name of the columns, they are supposed to be a date. The only problem is this X that appeared in here. So it was supposed to be January, but instead of 01, it became X1. So what you're going to be doing now, you're going to create this new data frame for country. So, oops, should be this one. So it's going to be like the other data frames, like you had the cases, but just for Argentina in this scenario. Now, what you're going to be doing, you're going to be getting these column names that have this X. you're going to be replacing whatever is X by a space, and then with a pipe, this is a command from the Lubridate, you're going to be converting this one to a date. So it's going to be month, day, year. That's the same way, that's the way that is the input. So here, here, if I just run this, I'm just getting the column names. So those are all the column names. So I have more than 280, because those are basically the number of days that you have in the data frame. Now I'm going to be replacing X for a space, so I don't have the X anymore. And here, down here, I'm converting it to dates. So it recognizes that we said the input would be months, day, year. So it's going to be converting to year, month, day. That's a way to use the dates in R. And here, you're going to be saving it in this. Now this is an array just for the dates. So it's just the same as before. We created this array date. The next thing that you're going to do is to now stack. If you have a country that has provinces, different provinces, so different from Argentina, Argentina just have one row, like Brazil, US just have one row. But if you work with Canada or Australia or other countries here, for example, Australia has several provinces in here that they have been separating the data set. So when you separate just the rows that has the country Australia, you're going to have this amount of rows. If you go for Canada, you're going to have one for each province as well. For China, the same. So some of the countries, they divide in provinces and some not. So just to, in case, just to work with the full country, you're not going to be working with the provinces. We are just stacking all the rows. So just doing a cumulative sum. In the case of Argentina, nothing is going to happen. It's going to be basically the same as we had before, because we just had one row. The only thing that the output of this is going to be an array. And this is a cumulative. So you can see the number is always increasing. It's not varying up or down. It's always increasing. So the last number that you have here is for November 4th. That it was yesterday. So we have 1.2 million cases in Argentina accumulated. That was confirmed since the beginning. Here, we're just calculating the difference of them. And here, I'm just including a 0 in the beginning, just a padding. So you're going to have the same number of elements as before. Now, with the diff cases, if we just plot this one in here, now we have the variation, how many we had per day. So those are the new cases per day. And here now, I'm just going to be combining the dates and the different cases. I'm going to be creating a new table or a new data frame where the first row is going to be the dates that we computed it in here. The second row is the cases or the new cases per day. So we're going to be calling this daily. When you run this, we create a data frame. So if you just check the daily, now we have this data frame. So we have the date from the beginning. That's the first day we have here is January 22nd until today or yesterday in this case. If you want to see like only the 5 first rows or whatever you want to see, so you do the head of the data frame, for example, the daily, and how many rows you want to see. Let's say 4. I want to see 4 rows. So when I run this, just see only the 4 first rows. If I want to see only the 4 last instead of a head, I use tail. So now we see the 4 last days. So the last one being yesterday. Here, I'm just going to be doing a plot of the daily cases using the ggplot library. So I'm just going to plot the date, the cases, just a line, and just to see how it is a time series for Argentina. So that's here on the side, on the right. So it started very slow and then it starts to increase the number of cases of Argentina. So first thing that you can see, you have seasonality in here. We have a trend. So this is a non-stationary time series. So it starts to increase until a peak here, sometime in October. And now it starts to decrease. And you have the seasonality. Those are usually weekend effects because the number of reports during the weekends, they usually are lower. And then a big jump during the week. We're going to do the same thing in here now for the death. So I'm just going to select everything and run to the end here and plot the number of deaths per day in Argentina. So now those are the deaths. So we have one day that has a big jump, probably because they had accumulated reports that all came to one day. So not that more than 3,000 people died in one day, probably just the reports that came in one day. And what I did here in the daily data frame, I just included a new column for the number of deaths. So you're going to have the date, the cases, and the death. And you can see here that are recognizing this column as a date column and all the others as double. So here, a thing that I'd like to do is just to do a plotting of the cases and the death together, but with the plotly. So it's going to be an iterative plot. So I'm just going to run these, and then I can go to the details. Oops, I selected, should not select. I run these. So you're going to be creating this plot on the right side. Yeah. So in blue are the number of the new cases that are related to this left y-axis, and in orange are the name of death that are related to this right axis in here. And you have the date. The advantage of using Plotly is now that you have iterative plot, you can see what each point represents. We can zoom and see how is the behavior of each part. You can pan in and just go around and see. For example, this large spike here of the depth was October 1st. So I don't know, is October 1st some kind of holiday or after a holiday in Argentina, Daniel?
No. No.
No. So probably it was just a cumulative of the previous months, something that all came in this day. So it's not a more dangerous day. And here, for example, we have the day that had more cases, around a little bit more than 18K. So it was in October 21st. And after that, the number of cases, new cases in Argentina is decreasing. So, and this is how you do a Plotly design. First you have to call the Plotly function, and then which data are you using here? So the data that you're using is the daily, is that a data frame that we just have the time series and those two columns. So after that I pipe, so the output of this is going to be sent in here. So I'm piping, and then I'm adding lines. So this is another function from the Plotly library, and I'm saying that the X is going to be the till date, means it's going to be the column name date from the data that was included in here. So as it was a data frame named the daily, so the X is going to be till date. So the X is going to be this column. The Y is going to be the cases. So I'm plotting this blue one. I'm going to be naming it as new cases. So when I name it and I include the legend, that's the name that's going to appear in here. So you can even turn off. If you just want to see the depth, you can turn off or turn on back. What is the type of we want to do of the fill? In this case, I selected to be the fill from Y to 0. I wanted to have this blue fill on the back here because I found it's nice. But if I just comment this part and run again, you're just going to have now a line plot without the fill. So I like the fill because it's easier to see what's happening to your data frame. The alpha is the transparency of the field, and the line, we have to include a list of parameters in here. The only thing that I'm changing is the width, I'm including as one. So let me just run again to go back to what we had before. And then I'm adding the second line, that is going to be the date for the X, and Y is going to be the number of death. And the only thing different that I'm doing here is I'm including this parameter YX, and I'm saying that is the Y2, means that I'm going to a different Y-axis, not the same on the left one. So after I add the lines, I have to change the layout of this. It's just changing the theme and some modifications that I have. So I'm just including the title of the plot. So I'm just using this other function named the string glue. So the country is going to be changed automatically by the one that we select in the beginning. For the y-axis 2 here, that's going to be on the right side. We say that's going to be on the right. It's going to be overlay y, and the title and the range that you're going to be selecting here. And the y-axis, that's going to be on the left. It's going to be also receiving all this information. And the x-axis is just going to be the title and the legend. What I'm doing here, I'm just including the legend, the title of the legend. So this symbol here, it's a HTML tag, that means bold. So I'm just saying that the title is going to be in a bold format, and I have to include it as a HTML tag. And this is just the location to be on the top left. Okay, so let's start to do our time series decomposition. So this plot here actually came from the time 2K. And this is just how we're going to do our decomposition of this time series. We're going to be using just the cases for the analysis, so on. You can do for that after if you want to. So what you're going to be doing here, we have the observed data set. Those are the daily cases of COVID-19 in Argentina. This is the trend that it's being calculated in here. The seasonality that we said here in frequency, it's going to be 7 days. We are saying to calculate the trend with information of 2 weeks. Basically, it's just a moving average of 2 weeks. You can understand that. And this is the reminder. That's the difference when you get this one and this sum. And subtract to this, you get this differentiation. This happens because the seasonality doesn't keep the same amplitude the whole time. If you go back to the previous plot, you can see the seasonality is increasing the amplitude in here. So this is called actually a multiplicative decomposition. When the trend increases, the seasonality increases as well. So this is not additive decomposition. So in this one, in this plot diagnostics, it's going to be calculating the additive decomposition, but this is a sign saying this is not an additive decomposition. It's a multiplicative one. Now here, we are going to start to work with our time series. So first, to train our and see, evaluate if your time series is doing, if your forecast is doing fine, you're going to select a period of time in here in the end to be our training set. Here I'm just saving an array of cases. That's going to be just the title, because I'm going to be using often in here. So if I want to create an array, I use this command C, means concatenate. So I'm concatenating just these two, and what I did, I just created an array, date and cases. I'm going to be using from this Modeltime, this time series split. So from the data frame that has the column names, cases, that's going to be date and cases, I'm going to say that our testing part is going to be the 3 last weeks of our data frame in here. So we're going to create this object here, named the splits. So it's an object from the Modeltime. So it contains a lot of information. What is the data, original data? What is the index for the training? and what are the index for the testing. So, and that's how we're going to be doing the plots. And in here, you're just getting our splits and our creating our plan for the times split. So we basically are going to create a new table. Whatever is training, we have the date and the cases. And if you get the last 3 ones, you're going to see that the key is going to be changing to testing. And here, this is a plot from the time 2K that you're going to be plotting those time series CV plan. That means the cross validation. So when you just be plotting this, it's going to be again another plotly style, and that's just our plotly. So we have our training that's going to be in black, and the testing are those red ones. So we're going to create our forecasting and see if you're doing well for these ones. And we have even the slides in here that can include from this one. So now we're going to be fitting our models. So that's how you're going to be using the model time. It's kind of similar in how you do for the scikit-learn. We're going to create our model. So this is a function from the model time named ARIMA regression. Means that you're going to be creating a ARIMA model. And I'm not including any other parameter inside here. I'm using all the default parameters. But if you want to learn more about this, just go question and ARIMA _reg, and if you press enter, you're going to have here in your help area tab all the explanations and everything that you can do, all the parameters that you wanted to change in here. But in this case, I'm just going to be using these ones. And then after I know that I'm using this model, ARIMA, I have to set an engine. Means for each library, I want to use the ARIMA one. There are several libraries for ARIMA, and the model time supports a few of them. So I'm saying that I'm going to be using this ARIMA. This ARIMA is going to search for you what are the best parameters for the PDQ, lowercase PDQ, the uppercase PDQ, and the seasonality. And here, by the end, I'm going to be fitting where the number of the cases is going to be in function of the date. This still means that's going to be in function of the date. And the data is going to be the training part of the splits. So when I run this, so it's going to take a couple seconds, it found that 7 observations per 1 week. So means that the seasonality is 7 days. And when you plot here the model ARIMA, that's the ARIMA model it actually found in here. So the SARIMA model in this case, because you have the seasonality part. So it was for the ARIMA part, for the non-seasonal, we had an auto regressive part of component of power 2, 1 differentiation, and 1 moving average. And for the seasonality part, we didn't need any autoregressive. We had to do 1 differentiation and 2 moving averages. And the seasonality was computed to be 7. Those are some of the coefficients that you have for all the parts and some of the metrics that it used to determine those parameters. Here it's commented, but you can do the same thing from the Facebook Prophet model if you want to. That's something that you can test at home. So, but I'm not going through this too much. And here now we have to calibrate the model before plotting and doing the predictions over our testing part. So first, the model time requires that your model that created is converted to a model table. In this case, we just have 1 model, the model ARIMA, but you can have several models in just 1 table, and it's going to run automatically all of them for you. So now this model table, we have just 1 table from this ARIMA with this information. Now you're going to be calibrating the model for the testing data set. And that's what we have. Now we have the test. And what is our data in here? Actually, it's already computed some ideas in here. Now we're going to get our calibration dates. You're going to be doing the forecasting for our whole data set in here. That's how it works to do the plotting for the testing. And then you're going to just be plotting. So you're going to be basically plotting our data over the testing part. So now, if you run this, those are our predictions for this part. So let me just give you a zoom here. It was following some trend that was increasing. The seasonality captured quite well, but it couldn't capture that in the last 3 weeks. Basically, in the last 2 weeks, the number of cases started to decrease because it didn't have this information before. So it couldn't predict that it was decreasing like that, the trend. So it actually created a model that it's quite, it's still increasing in the trend. It's increasing, it's lower, but it is still increasing compared to the previous one. And here, we are just computing some metrics that you can do, like the mean average and the RMSE and all the others. So if you have several models in here, in this case, we just have the ARIMA. If we uncomment this, for example, run in here, you're also going to be creating this Prophet model. Then we uncomment in here as well. So now we have a model time that has both models. It's going to be calculated for both. And now we have the plot in here. So now we're going to have a plot, one for the Prophet, that's going to be the red one, and the green is the ARIMA. So if you see, compare them both, they actually did pretty similar to each other, with the SARIMA actually have a little more variability in the seasonality part, but they are quite similar, if you see like that. And if you compute here the calibration, and you see the table, which model did better, they both were, again, very similar. You can compare them, but the ARIMA did slightly better than the Prophet. So just a way to compare and choose which one that you're going to use. Now you're going to be refitting our model for the whole data set, and then you're going to be doing the forecast for the next 3 weeks of data. So we just get our calibration data set. We're going to use this model refit for the whole data set, and then the forecasting here. This is the function model forecast. The age is going to be for the next 3 weeks, and the data that you're going to be including is our cases. So again, this is just the plot. This is a function from the time 2k, if I'm not wrong. And you can, but it's going to be creating basically a plotly function plot that you can actually change after with the layout of the plotly. So now, if you're going to do the predictions for the next 3 weeks, that's how it's predicting using both models. So actually, when you are using this information now that you're refitting the data, that we know that the number of cases is decreasing, the ARIMA, it's actually continuing to calculate this decreasing to be a little more optimistic than the Prophet model. Prophet is decreasing, but way slower. So I hope that the ARIMA or the SARIMA model is correct for this country. Another thing that when you have your data, I'm just suggesting when you download that maybe you can use other models using in the Modeltime, but can you use other models inside it? Can you use Prophet plus actually busting, Prophet plus neural network, and we have a lot of things that you can use in the Modeltimes. And try another country. For example, if I try Brazil, because I'm from Brazil, and run everything again. So I made it run. I asked for, oh, that happens sometimes, don't worry. I think I exploded my RAM memory somehow. So now I'm just gonna run this. And now I'm gonna have the final predictions for Brazil, for both model, for the SARIMA and for Prophet. So it's plotting everything, it's running everything. So let's see what's gonna be our final plot. Yeah, so those are the predictions for Brazil. So in both scenarios, it's predicting that it's decreasing. The SARIMA model has high variability. What makes sense because in Brazil we have a high variability also for the weekends. If you look for the table of which model performed better in this scenario, it was a little, now the Prophet apparently did better for this type of data set for Brazil. So that's why it's nice to have like a comparison so you can see which model worked better for each one. So when you create an app or something like that, you can say, oh, this is the best model. So this is the one that I'm gonna be plotting for the user. Okay, so this is the part of the coding that you have to present today. I'm just gonna go back to the presentation. So I just have some closing notes and what you're gonna be doing in the future. So for the next lab, you're going to be also doing the impact working with R, but you're going to be doing an impact analysis. You wanted to see what was the effect of the COVID-19 pandemic to the oil industry. So we're going to use in the data set without the 2020 year to predict what was supposed to be the price of oil and the production in 2020 and compare to the real case. And we're going to see what's the impact, how much of was the loss only due to the COVID pandemic. And after that, you're going to have an end of the year break. So the next one is going to be the last lab of the year. And after that, you're going to have a break and you're going to be returning sometime in January. So that's what we have for today. If you have any questions, please, now it's time to ask. You can unmute and ask, or you can send even a message. You might be getting some messages in here.
Yeah, I was going to ask a couple of questions. That was very nice talk, Marcelo, because I've never looked at the ARIMA or SARIMA. I know a lot about, I think most of us in geophysics know about the ARIMA model, but
yeah,
we rarely get into ARIMA because that's a different area that you're forecasting. But it's I'm sort of struggling to think if there's any applications in seismic analysis or well log analysis for this. Yes. And you know, I suppose the only thing we have with a trend would be a well log, but it's not a very predictable trend. I guess I could ask Daniel if he can think of any applications.
I think for things related to reservoir, wouldn't you have like you were thinking about well logs? I was thinking something similar to, like, for example, if you are looking at a reservoir, combining information, for example, about phases or something like that.
I mean, you could forecast, but there's really not enough. I mean, you could do maybe time lapse or something, but there's really not enough information. That's the big advantage the people in, you know, with when you're working with worldwide populations, you've got so much data to work with. Whereas when it comes to forecasting in our business, we don't have that much data.
Right. Well, one thing I was thinking, maybe not from the point of view of geophysics, but when you do this type of forecast, the problem that you have with the prediction is your time series is too short, right? So basically you're trying to predict the decay, but you only have a small portion of half a cycle, right? So it's not possible to do a prediction with such a low, I mean, normally you need at least half a cycle, even with these methods. If you are using Fourier, you would need even more. So I guess what improve predictions like this if you could combine different countries, right? So then, for example, you take Canada, where the cycle start, or Europe, where the cycle start much earlier, and you combine all these different time series. So then the model can capture a periodicity in the waves, like first wave, second wave, and then it can use it for other countries. That will probably give you a much more accurate prediction.
Yeah, I was just noticing on the chat, Jeff Grossman suggested well productivity versus time, and Marie Marquez said, "Can you forecast microseismicity?" So there might be some good applications.
That could be something very nice to use that. I see a lot of people using this forecasting, most for the business area, for the production, and also trying to understand what type of variables that will change in the well situation, like the type of mud or the pressure or everything that changes your forecasting, your production. So they do this kind of analysis as well.
Interesting.
I was also thinking in gravity work, because you got tidal. There's in microgravity, you've got tidal effects, and of course in magnetics, you also have the electric variations from solar.
Yeah. So diurnal effects.
Yeah.
Interesting.
Yeah. So.
I mean, your application was very interesting, but I think we're all kind of geoscience geeks here.
Oh yeah, that's just to show what is this model, how it works, and then we can think about other type. So for the next one, I'm gonna use those same methods to do the impact analysis. So it's one application. What's for the business side a little bit.
We looked at this model for a plant optimization problem. We had a plant that had cyclical dumping and was just trying to understand if we could predict from the pi tags we had. If we could predict it, then we had the right information in the pi tags to fix it. But anyway, that one is still in progress.
It's interesting.
Okay, that's another thing to do. About forecasting microseismic, I think that's possible if you use like this SARIMA exclusively that I'm using. It's using only the history of the own time series to try to predict the future. But you can use other variables, external variables, also to improve this. For example, we have some changing points, holidays or things like that, that might change how the COVID behaved in different countries. In the case of microseismicity, we could use other information for pressure and other stuff and try to predict in time when it's going to happen as well. Yeah, I think that's a good application. We could look into that.
Jeff says multiple suppression. That might be a good one too.
That could be.
Yeah, one other application of predicting like this is when you work, for example, in some electromagnetic methods, like things like where you have to record very slow electromagnetic waves, like my experience, for example, in magnetotelluric, we have problems like this, where you have very, very short periods, right? And then you have areas where you have to predict missing information, but because the number of cycles you have is so short, then the only thing you can do is something based on autoregressive models or ARIMA too. This is kind of the basics of maximum entropy algorithms for spectral estimation, right, Burke?
Right.
Okay.
Good stuff. Thanks.
Okay, so I think if you don't have any more questions, I'm going to stop the recording here. So I'm going to thanks everybody for coming, for participating. So hopefully I'm going to see you in the next 2 weeks.
So you wanted, we need to chat about what I'm going to do in the new year there, Marcella, too.
Oh, okay.
Because you had contacted me on LinkedIn, and I always say it's always better to do it directly on email. I work better on email than LinkedIn, but
Oh, okay. No, no problem.
I've got some ideas for the new year if you want to run them by you.